So now what we're going to look at is how we can apply derivatives really to functions themselves and see what derivatives tell us about a function, and more specifically the graph of the function. And so let's start with the idea of what it means for a function to be increasing. All right, so we have a relatively formal definition in order to characterize what we probably think we know about what it means for a function to be increasing, but let's look what it says. A function f is increasing on an interval if for any two numbers x1 and x2 in the interval, x1 less than x2 implies f of x1 is less than f of x2. This is a lot simpler than it sounds. It's just saying that if you take x1 less than x2, and if we have an increasing function, so maybe something that's increasing, going up to the right, then we'd be saying the value at x1 is less than the value at x2. Makes sense. Right? So now, if we said, all right, well, what is a decreasing function? So a function is decreasing on an interval if for any two numbers x1 and x2. In an interval, x1 less than x2 implies f of x1 is greater than f of x2. So again, if we take x1 less than x2, now if we have some sort of decreasing function, then if x1 is less than x2, then f of x1 is bigger than f of x2. So that's just a way that we can say it more formally. All right, so here's the connection that we really get to right now. We would like to be able to connect the increasing or decreasing nature of a function with its derivative. Okay, so this important theorem tells us that if f is a function that is continuous on the closed and differentiable on the open, then the derivative being greater than 0, so a positive derivative for all the x in a certain interval means that f is increasing on that interval, while a negative derivative would mean f is decreasing on that interval. And a derivative of 0 would mean that the function is constant on that interval. Now this makes sense because remember the derivative is telling the rate of change. If the rate of change is positive, then the function should be increasing. If it's negative, then it should be decreasing. And if it's 0, then it shouldn't be changing at all and hence be constant. And if we go back up here, what are we really saying? We're saying if we look at these graphs, notice everywhere in this, for this increasing function here, we have tangent lines that have a positive slope. While for this decreasing function here, we have tangent lines that have a negative slope. So that's the idea. Now let's put it and see how we use it in an example. So identify the open intervals on which the function is increasing or decreasing. All right. So in order to do this, we're basically going to try and find out where the derivative is positive, where it's 0, and where it's negative, and that'll tell us everything. So we're going to need the derivative. That's simple enough here. F prime of x is 2x minus 2, or in other words, 2 times x minus 1. Okay, so we want to know the critical numbers of f. In other words, we want to know where the derivative is 0 and where the derivative is undefined and the function is defined. All right. So in this case, it's pretty simple. We see that x equals 1 is a critical number because the derivative is 0 there. And there are no places where the derivative is undefined. It's a nice polynomial. Okay, so what this has told me is that I have only the critical number x equals 1. So what are we going to do with that? So what we're going to do is we're going to take a number line, and this number line is going to tell us about the sign of f prime. Okay, so on the number line, we're going to put any critical numbers. We'll also put any place where the function is not defined, but there isn't any of that here yet. So we're going to put just the point 1, because that's our only critical number here. And then we're going to go into each region and see what is the sign of f prime. So I'm going to go back to f prime right here and think about, take any number from the region less than 1. All right, so if I were to take, say, some 0, so I'm just doing it lightly there because I don't really need it there, I just want to identify where I'm taking a point. So if I put 0 in, I'd get 2 times 0 minus 1, I'd get a negative result. All right, so I get negative numbers there. If I go above and take maybe 2 and plug in a 2, then if I plug it into 2 times x minus 1, I'm going to get a positive number. So this is showing me that the derivative is negative when you're less than 1 and positive when you're bigger than 1. And we already know from what we did before that it's 0 at 1. Okay, so remember, a negative derivative, what does that tell me about the function? Negative derivative tells me the function f is decreasing. So that's the sign of the derivative telling me about what the original function is doing. Derivative positive tells me f is increasing there. Okay, so that's pretty much given me everything I wanted to know. All right, it's telling me that f is decreasing on this interval less than 1, so negative infinity to 1, and f is increasing from 1 to infinity. All right, so I've been able to find out exactly where the derivative is increasing and decreasing. Okay, let's take a look at another one. All right, y equals x squared plus 4 over x. Okay, the first thing I'm going to do is I'm going to note that there is a discontinuity at x equals 0. All right, that might be important later on. All right, so if I'm going to take this function, I'm going to need to know the derivative. All right, so quotient rule, derivative of the top 2x times the bottom x minus the top x squared plus 4 times 1 is the derivative of the bottom over the bottom squared. That's going to give us 2x squared minus x squared minus 4 all over x squared. That's going to give us x squared minus 4 over x squared, which factored would be x minus 2, x plus 2 over x squared. Okay, so again, I want to know two things. I want to know where is the derivative 0, and where is the derivative undefined, and y is defined. Okay. All right, so the derivative being 0, I can see back from my derivative here. Its numerator is 0 and x is 2 and negative 2. Where is y prime undefined? Well, it's undefined at 0, but the original function was also undefined at 0, so that's not really a critical number. It's going to be an important place, but it's not technically a critical number. Okay, so now I have the information to do a little derivative chart. Okay. So I'm going to put on this chart the critical numbers, -2 and 2, and I'm also going to put the 0 here, and I'm just going to make a note to myself that that's there because it's a discontinuity. It is not a critical number, and it's not going to, but I have to consider it because it might break up some intervals of where things are happening. So the idea is I'm trying to make all these intervals where the derivative is only positive or only negative on that interval, so I have to include anything like a discontinuity as well. All right, so let's go back to our derivative, our nice factored derivative there. And so I want to look at what sign I get when I plug in some numbers. Now the denominator there isn't going to change anything because it's x squared, so I'm looking at the numerator. All right, so if I go into the interval here that is less than -2, if I put -3 in, I would get a negative times a negative, so I'll get a positive overall. If I put -1 in, I'll get negative positive, so I'll get negative. If I put 1 in, I'll get negative positive, I'll get an overall negative. If I put 3 in, again, I'm just picking numbers from these intervals, I'll get positive, positive, I'll get overall positive. And this is going to tell me what y in this case is doing on these intervals. So if it's positive, that means y is increasing, negative y is decreasing, negative y is decreasing, and here y is increasing. So I could say that y is increasing on -infinity to -2 because of this interval, and to infinity, while it's decreasing on -2, 0, and 0, 2.